Morning, everyone. So, at the outset, I thank our director for providing me this opportunity to present on the historical background of electrochemistry, which is being a part of the electrochemistry past, present, and future. So, myself and Lakshmi Narasimhan, working at CSIR Central Electrochemical Research Institute, which is one of the 38 national labs of Council of Scientific and Industrial Research. So CSIR-CECRI was founded in the year 1948 by the great visionary Dr. R. M. Chettiar, who donated 300 acres of land and 15 lakh of rupees in cash to establish this organization. So it started functioning from the year 1953. And currently, we are about 110 scientists, and we have 100 PhD scholars and more project staff who support the R&D activities of CICRI. So our campus is very nice. So we have a lot of peacocks that makes our campus more beautiful. So coming to my background, so I have been working on functional materials for energy and environmental applications. So I obtained both bachelor's and master of science degrees in chemistry from University of Madras, and I did my PhD from Indian Institute of Technology Madras in 2005. So I joined at CSIR-CECRI in 2009. So with the basics, my degree in PhD is in solid state chemistry and material science. So I use this knowledge to design and synthesis of materials and to understand the structure property relations in various materials. So those materials encompass photofunctional materials that again include phosphors, that's inorganic luminescent materials used in white light emitting diodes, and photocatalyst used for environmental remediation applications, and also the photoanodes used in DSSC, that is dye-sensitized solar cells. So I have been also working on energy materials, so like batteries, lithium-ion battery materials, and supercapacitors, dielectric and magnetic materials, which comes under the electroceramics. So the focus on all these materials is the tuning the properties of functional materials, that's materials with specific functionalities. So this can be done by controlling or understanding the crystal and electronic structures of the materials and their composition, and tuning the morphology, that is the size and shape. So if you control the size and shape of a material or reduce them at the nanoscale or nano dimensions, so you are going to get some extraordinary properties of any materials. So this is with this background. So let me move on to the what electrochemistry. That's what we are going to talk about today. And my colleagues also will present more details on specific applications of the electrochemistry. So electrochemistry is a chemical phenomena associated with charge separation leading to charge transfer, either in homogeneous solution or it can also happen at heterogeneously at electrode surfaces. So this, for example, if you take a zinc rod dissolved in zinc sulfate and a copper rod in a copper sulfate solution, if you connect, the zinc starts dissolving as a zinc 2 plus, and the two electrons released goes to the other electrode where the copper ions from the solution deposits at the copper. So this is the galvanic cell. So understanding this phenomena is constitutes the electrochemistry. So this looks so simple, but there are a lot of interface happens at this level, which is what makes electrochemistry a unique field. So also electrochemistry is interdisciplinary and an international science. So electrochemistry lies at the crossroad of many disciplines of science and technology. And it is very important. So why it is important is because understanding the electrochemical processes is useful in several other areas. For example, in the analytical chemistry or energy conversion and storage, biological sciences and medicine, material science, and micro and nanoelectronics. So in all places, the understanding the phenomena electrochemical process is going to be very useful in making any advancement in those fields. So the modern electrochemistry. So it can be classified. It can how it was developed. So according to Gallus, so it was evolved through different periods. So the first period starts from beginning of this field and to the end of the 19th century. The second period is between 1901 and 1945. The 19 years 1946 to 1965 is considered as the third period, and the fourth period is between 1966 to 1990, and from 1991 to present day is classified into the fifth period of the development of modern electrochemistry. So that means there has been a lot of contributions made in various periods by many great scientists across the world to make this field the modern electrochemistry branch of science as a new field. So let us look into the 19th century. So even though the concept of electricity was developed much before in by the physicist, and it was the Galvani who first made the using the frogs. So he found the electricity as frog electricity or the biological electricity. But it was the Alessandro Volta, so who first came up with the electrochemical potential series of metals in 1793, and he also made a prototype of battery in 1800. So to remember his contributions, now we have the unit volts is because of the Alessandro Volta. And then came the Humphrey Davy. So he used the electrolysis process to obtain sodium and potassium in the year 1806. And then came the important contributor, Michael Faraday. He has made a lot of contributions, not only to electrochemistry, also to the magnetism. So he has been the considered as a father of electrochemistry, and he has made the important electrolysis laws that relates the amount of substance deposited during these electrolysis processes. So this contribution was mainly made in the year 1833. Then Robert Bunsen used the electrochemical process to produce magnesium and aluminum from the molten salts. So in the years between 1852 and 1854, and following the electrical double layer model, which was first conceived by Hermann von Helmholtz, as we have seen, there is a lot of process happening at the electrode and the electrolyte solution interface. So whenever you keep any material on a solution, so there occurs an interface. So that can also have ions or the solvent molecules. So whenever charge transfer happens, all this can contribute. So that's how this double layer model was first proposed by Hermann von Helmholtz in the year 1853. And the year 1859 has seen another important development, that was the lead acid battery by Gaston Plante. So what we are using today also for the storage of energy. So as a lead acid batteries. So then Leclanche made the battery in the year 1867. Then Friedrich Kohlrausch, who proposed the law of independent migration of ions in the year 1876. So another important contribution came from Svante Arrhenius, who has developed the theory of electrolytic dissociation in the year 1886. Then Van Hoff produced the theory of solutions. Then in electrochemistry, there is a famous equation called Nernst equation to predict or to calculate the electrochemical potential of a cell. So which was known as Nernst equation, developed by Walther Nernst in the year 1889. And in the year 1889 itself, Friedrich Oswald made the dilution law. So all these contributes to understand the electrochemistry. So further, in the first half of the 20th century, so Tafel equation, so which is also one of the famous equations in electrochemistry, was developed by Julius Tafel in the year 1905. At the same time, Gilbert Lewis, so he has shown or demonstrated the thermodynamic concepts of activity and activity coefficients in 1907. Then the Sorensen introduced the pH scale in 1909, and the double layer model, which was developed earlier by Helmholtz, was further developed by Goy, Chapman, and Stern by taking into account of different parameters. So that's how they developed the theory of electrode electrolyte double layer in the years between 1913 and 1924. And then the Debye-Huckel theory of strong electrolytes was proposed and developed in 1923. Then again, one more equation which is famous in the electrochemistry is known as Butler-Walmer equation, so which was developed by Butler, de and Walmer. So this relates the concepts of slow electrode reactions. So how to understand them? What is charge transfer behavior? So that's what developed between 1924 and 1930 by Butler-Walmer. So further to do the Lars Onsager, who made a lot of work on conductivity, that's known as the Onsager equation in the year 1926. Another important name in the electrochemistry is Alexander Frumkin. So he studied the thermodynamic, he produced thermodynamic theory of surface phenomena on the phase boundaries and adsorption of organic compounds in the year 1928. And also he demonstrated or he studied the influence of the double layer on the rate of electrode reactions in 1932. Then the acid-base theory was developed by Bronsted and Lowry in the year 1928 based on the proton, that's H plus ions, and also the quantum mechanics, how to apply them to the understand the electron reaction were made by Gurney in the year 1932. I'm sorry I could not get the picture of Gurney at this moment. So then the second half of the 20th century, further important names comes here like Isaac Kolthoff, so who made a lot of contributions to the electroanalytical chemistry, made, for example, the conductometric and potentiometric titrations used in analytical chemistry, and the polarography for trace metal analysis in environmental samples, and also the ion selective electrodes. So another important name is Heinz Gerischer, so who studied and defined a lot of concepts behind the electrochemistry and especially the photoelectrochemistry of semiconductor electrodes. So that made the contribution to understand today's the photovoltaic cells and the solar cells or the photoelectrochemical cells for used in water splitting or hydrogen production, etc. So some more names which are most related to the CSIR-CECRI is by Dr. K.S.G. Das, who served as a director of CSIR-CECRI in the years 1958 and 1967. So his contribution goes to making the alternating current effects on adsorption and electrode kinetics. Also, he independently developed this kind of AC effects on polarography that's known as the tensometry technique. So another important name which relates to CSIR-CECRI is Professor S.K. Rangarajan, who also served as director of CSIR-CECRI between 1989 and 92. So his theoretical modeling of interfacial phenomena happens at various electrochemical processes. So similarly, the Rudolf Marcus, who proposed the theory of electron transfer in various processes happening. Then in the second half of the 20th century, the few more names which are very important is Brian Conway. So who studied the electrified interface, rechargeable batteries and electrochemical capacitors, where on which he has written a book which is known as a standard book for electrochemical capacitors. So then J.O.M. Bockris, so who tried to understand the electrokinetics and contributed a lot to this kind of work, and he has made a lot of volumes on modern aspects of electrochemistry. More importantly, he also contributed in developing another model on the double layers, along with Devanathan and Muller. Again, Devanathan has also served its CSIR-CECRI for a short while. And similarly, the associated another name with J.M. Bockris is Amulya K.N. Reddy, who served as a senior scientific officer who worked here at CSIR-CECRI between 1958 to 1961. So he and Bockris has contributed the famous textbooks, the two volumes of modern electrochemistry. Then coming to the batteries and fuel cell research, the name Carl V. Kodesh is another important one whose contributions are very important in the field of electrochemistry of batteries and fuel cells. So these are only a summary of the main contributors. There may be many names which are also involved in specific techniques and other methods developed. For example, we can include Alan J. Bard, who has made a contribution to the the electrochemical microscopy. technique and the electrochemiluminescent techniques. So similarly, in this development of electrochemistry, so between the different periods, so there are several methods also developed or the electrodes have been developed. For example, the sand equation used in chronopotentiometry was made in the year 1901. And similarly, the Cottrell equation related with potentiostatic method is made in 1902. And Nernst used the hydrodynamic voltammetry in the 1904. The glass electrode was first used in 1909 by Haber and Clemensewicz. And Herowski, the important contribution came from him using a dropping mercury electrode, and the technique is known as the polarigraphy in the year 1922. The pH meter was made by Beckmann in the 1935. Similarly, the potentiostat was by 1942 by Hickling, and microelectrodes were started being used from 1942 by Davis and Brink. And similarly, Harowski, along with Forage, made the streaming mercury electrode in the year 1943. And Randall's Herschler has made a measurement of electrochemical impedance in the year 1947. The Randall's circuits, equivalent circuits, are important ones in understanding the electrochemical process using the impedance techniques. Similarly, Randall Sevcik has made a contribution to the linear potential scan voltammetry in the year 1948. And similarly, the different electrochemical methods, for example, the traditional methods that have been developed between the periods 1 and 3 include chronoamperometry, it can be one and double step, similarly chronocoulometry, chronopotentiometry techniques, and linear scan cyclic voltammetry. Another one is rotating disk voltammetry, also with ring electrodes and other hydrodynamic voltammetries, and electrochemical impedance, as mentioned earlier by Randalls. So these techniques are also introduced in the period between 1 and 3, and staircase voltammetry and different voltammetries like staircase, square wave, AC voltammetry, or putting the alternating current on the polarography resulting in the tensometry technique. Similarly, stripping, pulse, and voltammetry techniques, and also the chromatopolarigraphy techniques. So these are the traditional methods of electrochemical methods have been developed between the periods 1 and 3. But the period 4 has seen a different type of method, that's non-traditional methods, that's combining electrochemical techniques with other spectroscopic techniques, because we want to monitor what's happening at the species produced during your electrochemical reactions. So, for example, we can combine the ultraviolet spectroscopy with electrochemistry, that's a spectroelectrochemistry, with the optically transparent electrode. So, if your electrode is transparent for the light to penetrate, and when you do an electrochemical reaction on these transparent electrodes, you shine a light from the other side, and also we can monitor the effect of this light or the electrochemical reactions on the species produced and the influence of this light on the electrochemical processes. Similarly, the other methods include ellipsometry and infrared reflectance absorption spectroscopy, surface enhanced Raman spectroscopy. These techniques also can be coupled with electrochemistry, and X-ray absorption spectroscopy, electroreflectance spectroscopy, X-ray diffraction method. So you can also use X-ray diffraction method in situ to monitor the batteries, lithium-ion batteries, how the cathode is changing or the process happening at the anodes. So what is the structural changes happening, and understand the structural stability of materials during the charge discharge cycling of battery materials. Similarly, second harmonic generation, quartz crystal microbalance, and also we can do electrochemical reactions at the electron paramagnetic resonance spectrometer or a nuclear magnetic resonance NMR spectrometer. Because when you do electrochemical reactions using a small electrode, so in this case, there are any radical species which are produced which are short-lived. So these can be monitored using the EPR spectroscopy or the NMR spectroscopy in revealing the mechanism of electrochemical reactions. So the period 5 has seen more on the imaging techniques. For instance, the scanning, tunneling microscopy, or atomic force microscopy, or scanning electrochemical microscopy. So these techniques can be coupled with electrochemical techniques electrochemistry. So to produce the different important materials. For example, so this is a STM image of a single crystal of gold, 5 nanometer by 5 nanometer dimension. So we can see the highly oriented arrangement of the atoms of gold in this surface. Similarly, we can use this STM technique along with electrochemical methods. So we can deposit 12 atom clusters of copper at 111 surface of gold. For here it is the gold surface. So we have a STM tip which was first dipped into the copper solution and kept at a potential more negative than the copper 2 plus copper redox potential, so that the copper gets reduced here. And this tip, when it was brought closer to the gold surface, the 12 atom cluster, so you can control them through again electrochemical techniques to deposit such nice structures to produce the coral of the 12 copper cluster on a gold surface. So such important techniques also can be possible. This has been seen by the fifth period of the development of modern electrochemistry chemistry. Similarly, the electrochemical topics which have been developed in the periods between 4 and 5, as we have seen already, the double layer models. And these are important because you can also study the self assembled monolayers and similarly interface between two immiscible liquids, understand the absorption phenomena and reactions at the surface attached to the reactants, and surface spectroscopic methods, non traditional methods, and progress in surface electrochemistry, and studies of the various interfaces using imaging techniques like we have shown in the STM techniques or AFM methods. Similarly, other topics include the voltammetry with the monocrystal electrode, that's a single crystal electrodes. So electrodes modified with various chemicals and impedance and noise analysis method, and to understand the medium and solvent effects on potentials of electrodes and electrode kinetics, electrocatalysis, and electrochemistry of redox enzymes and charge transport in biological systems, in vivo voltammetry and theory of charge transfer reactions. And one more important is under potential deposition, how you deposit the metals at the potential which is much below than their standard potentials. And more important contributions goes to photoelectrochemistry and electrochemistry of semiconductors and insulators that are being used in photo electrochemical cells. And similarly, we have used digital simulations to mimic or to simulate the complex electrochemical processing happens experimentally. So, for example, if you take more particular electroanalysis, so what are the separate branches, that is the topics that are developed under this includes ion selective electrodes and stripping analysis or electroanalytical methods for trace analysis of elements and electroanalysis in flow streams, ultra micro electrodes and sensors, biosensors and molecular recognition devices. And more applications also have been developed, have been realized during the periods 4 and 5. So examples include the electrolytic production of metals, the electrochemical nanotechnologies, bioelectrosynthesis, and environmental electrochemistry, electrochemical protection against corrosion, electrochemistry in medicine, for example sensors, biosensors and electrotherapy of cancer. And in the energy sector, so fuel cells and biofuel cells, and simple and rechargeable batteries, and solar energy conversion, and supercapacitors, and similarly the toxic waste disposal. And another advantage of electrochemistry is it can tie up with any branch of science and engineering or technology. So electrochemistry can coupled with physics to result in physical electrochemistry, where a lot of physical phenomena can be understood using this kind of combination. And similarly with biology, we have bioelectrochemistry, and quantum chemistry goes with electrochemistry to produce quantum electrochemistry. And as electrochemistry has been used in several analytical techniques, so we have a electroanalysis. So similarly in medicine, so we have medicinal electrochemistry. So with electronics and electrochemistry results in electrochemical physics, and material science with electrochemistry to go for materials electrochemistry, and with the technology or engineering like metallurgy. So we're using electrochemical techniques in these branches of technology produces electrochemical technology or electrometallurgy, And in environmental science, it can produce environmental electrochemistry, and computational electrochemistry also possible by combining computer science and electrochemistry. That means electrochemistry can combine with any topic. It doesn't matter whether we are a science background or we are engineering background. So we can use electrochemistry in any branches so that to understand and develop methods and materials which are being used for our society. So current and future topics, there are several topics. For example, if you look at bioelectrochemistry itself to understand the charge transport across various phase boundaries, membrane processes, biomimetic research, bioelectrocatalysis, or the electrochemistry of redox enzymes, bioelectrosynthesis, biosensors, these find application in medicine. Similarly, the surface phenomena and using nanomaterials, so we can use single molecule studies and molecular electronics, molecular junctions we can make, and new nanomaterials and their modifications, and further development of electrochemical scanning microscopy using these techniques. And also like STM and AFM can couple with electrochemistry. And selectivity in electroreactions and dynamics of components in the interface. Similarly, with modified electrode, that means you can modify electrode with a different material, for example, with carbon nanotubes or graphene to study the different catalytic properties, can make several composite electrodes or self-assembled molecular films for various biosensing applications and new sensors for different applications. Similarly, in the energy conversion and storage applications, so we have several batteries. So, for example, from lithium-ion batteries now focusing on sodium and magnesium-ion batteries, and fuel cells for both transportation and power systems, solar energy conversions, and organic semiconductors, solid and semiconducting materials, biofuel cells, and analogous to photosynthetic systems like nitrogen fixation and CO2 fixation, which are more important topics for considering the environmental issues. Similarly, you can use for clean electrochemical technologies and toxic waste disposal and corrosion and its inhibition. So, having seen all these developments in various branches of electrochemistry or modern electrochemistry, the CSIR-CECRI, Central Electrochemical Research Institute, being South Asia's largest electrochemical hub, encompasses all these activities in its R&D activities. The electronics and electrocatalysis group focuses on understanding the fundamentals happening at the interfaces. The electrochemical power sources involves in the research on the batteries, lithium-ion, sodium-ion batteries, or the fuel cells or redox flow batteries. And electroorganic chemicals focuses using electrochemical techniques to produce organic chemicals which are otherwise very difficult to stabilize or produce by conventional organic synthesis. In a similar manner, electro-inorganic chemicals can be produced like hydrogen peroxide or other kind of perchlorates using electrochemical techniques in an easier manner. And corrosion and materials protection focuses using prevention or mitigation of corrosion at the concretes or bridges under sea, water. And materials electrochemistry develops materials exploring materials for different electrochemical applications. And electrochemical process engineering uses electrochemical techniques in the removal of contaminants like arsenic or fluorine. And electroplating and metal finishing technology produces, for example, a cyanide-free brass deposition or copper deposition for environmental application and for the various applications of coatings. And electrometallurgy uses electrochemical techniques in extraction of various metals in large quantities using electrochemical techniques. So, with this, at this part of the lecture, I conclude how the electrochemistry has originated and how CSIR-CECRI is involved using the various aspects of electrochemistry. So, these are the references which have been used for this kind of preparation. And I stop at this moment for this part of the lecture. And thank you very much for your kind attention.